one of the greatest mysteries of science. Did anything exist before the universe? The Big Bang Theory states that our universe originated about 13.8 billion years ago, expanding from an unimaginably hot, dense state into the vast cosmos we see today. This beginning was marked by a rapid expanse of space, cooling, and the formation of the first particles and atoms. But the before moment, the time previous to this cosmic birth, remains shrouded in uncertainty. It's possible that time and space were born together with the Big Bang, a point beyond which our current laws of physics cannot peer. Yet human curiosity compels us to keep asking the question. Scientists and philosophers have long pondered whether the Big Bang was truly the beginning or just one chapter in a much broader cosmic story. In today's documentary journey, we'll explore what modern science can tell us about the origin of time, examine new discoveries that expand our understanding of the early universe, and consider bold theories that go beyond the Big Bang itself. Let's start with the fact that, according to our best scientific understanding, the Big Bang marks time zero, the beginning of the universe as we know it. In a single instant, all space, time, energy, and matter emerged from an initial singularity, a point of infinite density. In the first fraction of a second, the universe underwent rapid inflation, expanding faster than the speed of light in a space that was itself expanding. This set the stage for everything to come. 1 second after the Big Bang, the universe was a hot, opaque soup of particles. Within minutes, the first light chemical elements formed in a process called primordial nucleosynthesis. The early cosmos was extremely hot and dense, so hot that atoms couldn't yet hold together. Light or photons were constantly scattered by free electrons, meaning it couldn't travel far. For the first few 100,000 years, the universe was essentially foggy and opaque. As expansion continued, the cosmos cooled. And fast forward 380,000 years after the Big Bang, the universe had cooled enough for electrons to combine with nuclei to form neutral atoms. This moment, the epoch of recombination, changed everything. Now that electrons were bound in atoms, light could travel freely through space for the first time. The original fog lifted, and light burst across the cosmos. This ancient light still surrounds us today in the form of a faint glow from all directions, stretched over billions of years of cosmic expansion into the microwave range. We call it the cosmic microwave background, or CMB, and it's literally a picture of the universe in its infancy. By observing the CMB, scientists can see what the universe looked like when it was only 380,000 years old, practically a newborn compared to its 13.8 billion year lifetime. This is the oldest light we can observe, a relic image of the fireball of the Big Bang itself. Discovered in the 1960s, cosmic microwave background has been measured in increasing detail over the decades using satellites and telescopes. It carries a wealth of information. The speckled pattern of tiny temperature differences across the sky is not random. It encodes the seeds of the cosmic web that formed later. Regions that were slightly denser on this early map eventually collapsed under gravity to form galaxies and clusters. In fact, the CMB is a blueprint for future structure, showing the hills and valleys in the distribution of the original matter. It also gives insights into the cosmopolitan and shape of the universe. Decades of analysis have shown that ordinary matter, the stuff that makes up stars, planets, and us, accounts for only about 5% of the total content of the cosmos. The rest is dark and mysterious. About 27% is dark matter and roughly 68% is dark energy, according to measurements of the CMB's properties. Remarkably, new observations continue to refine this picture. In March of 2025, researchers from the Atacama Cosmology Telescope, or ACT, and the Princeton University released the most detailed images of the CMB to date, the clearest infant pictures of our universe yet. With 5 times the resolution of the previous full-sky map made by the Planck satellite, ACT's extensive survey data even captured the polarization of this ancient light. This polarization, this directional orientation of CMB light waves, it reveals how much matter moved in different regions of the young universe. Before, we got to see where things were, and now we also see how they're moving, explains Dr. Suzanne Staggs, director of ACT. These high-resolution images show subtle changes in the density and velocity of the primordial gas, the fine details of those early hills and valleys. This kind of data helps scientists answer long-standing questions about how our cosmos evolved from simplicity into complexity, and it's astounding. By measuring light that's traveled over 13 billion years, we can see the universe as it was just a few hours after its birth on a cosmic scale. If the CMB represents the thermal radiation of the infant universe, what happened next in cosmic history? After recombination, the universe entered the Dark Ages, literally. When the fog had cleared, the background glow gradually faded, and no new light had yet appeared because stars had not yet formed. This era ended when the first generation of stars ignited, likely around 100 to 200 million years after the Big Bang. These earliest stars, often referred to as population 3 stars, were probably massive, short-lived beacons that began to illuminate the young cosmos. They gathered in proto-galactic clouds, marking the beginning of galaxy formation. Astronomers have named this period the Cosmic Dawn, the time when starlight first banished the cosmic night. Today we're actually beginning to glimpse the cosmic dawn thanks to powerful new telescopes. The James Webb Space Telescope, launched in 2021, was built to observe the faint infrared glow of extremely distant galaxies. Because light from the early universe has been stretched or redshifted into infrared wavelengths, Webb's infrared eyes are perfectly suited to capture it. In just its first few years of operation, JWST has shattered all records, discovering galaxies that existed only a few 100 million years after the Big Bang. One such galaxy, whimsically named MOM Z14, was in 2025 recognized as the most distant galaxy ever observed. Its light comes from just 280 million years after the Big Bang. In other words, we see this galaxy as it was when the universe was only about 2% of its current stage. The light from that time had to travel nearly 13.5 billion years to reach us, and JWST's instruments finally captured it. Overall, since beginning operations in 2022, JWST has found more bright early galaxies than scientists had expected. This unexpected abundance has thrilled the community and raised fundamental questions about galaxy formation in the first 500 million years of cosmic history. Each new discovery of a high redshift galaxy adds another piece to the puzzle, helping us understand how the universe's structure formed in its earliest stages. For example, MOM Z14 galaxy, based on observations, was undergoing a rapid star formation phase at the time of its discovery. and its chemical composition, rich in nitrogen in relation to carbon, resembles the makeup of ancient globular star clusters in our Milky Way. This suggests that even in this very early epoch, star formation may have occurred differently than in later periods. These discoveries force astronomers to revisit their assumptions about how quickly small initial fluctuations, seen in the cosmic microwave background, could condense into fully formed galaxies. How could such massive, bright galaxies form so quickly? Were stars and galaxies forming more efficiently than our models predict, or is our understanding of cosmic chronology incomplete? As new observatories come online, we expect to peer even closer to the Big Bang, possibly observing objects from the era of the very first stars. However, no matter how powerful our telescopes become, they will never be able to see what happened before the Big Bang. For that, we must turn to theory. Over billions of years under the influence of gravity, matter in the universe gathered into a vast cosmic web. Galaxies are not evenly distributed. They form filaments and sheets with large voids between them. This web-like pattern can be traced back to the initial fluctuations seen in the cosmic microwave background. Generally, our cosmological models based on the Big Bang theory and an expanding universe filled with dark matter predict that there is an upper limit to the size of large structures. The cosmological principle is a cornerstone of modern cosmology. It states that on very large scales, the universe should be roughly homogeneous, without enormous clusters or distinct patterns dominating one region over another. Essentially, when averaged over hundreds of millions of light years, every part of the universe should look more or less the same. According to standard theory, the largest coherent structures that can form should be around 1 billion light years across. That's why astronomers were surprised to find structures that far exceeded those dimensions. In 2024, researchers discovered a massive ring-shaped pattern of galaxies and galaxy clusters they dubbed the Big Ring. It spans about 1.3 billion light-years in diameter and roughly 4 billion light-years in circumference. We observed this structure as it was around 9.2 billion years ago. Essentially, that's how long its light took to reach us. Intriguingly, it lies near another colossal structure known as the Giant Arc, which itself stretches an astounding 3.3 billion light-years. To put these scales in perspective, the Milky Way's own supercluster is only about 0.5 billion light-years in diameter. The Big Ring and the Giant Arc are truly leviathans on the cosmic stage. Moreover, a detailed analysis suggests that the Big Ring isn't really a ring. It may actually be a spiral or corkscrew shape twisting through space. If we could see it with the naked eye, which we obviously cannot due to its distance and faintness, one researcher said it would appear about 15 times wider than the full moon in our sky. This feature defies explanation using our best theories about the universe. The Big Ring is too large and too structured to be easily explained by the usual mechanism of baryon acoustic oscillations. Those pressure waves in the early universe could lead to a large-scale galaxy distribution, but they should appear as roughly spherical shells, not elongated rings, and not on this massive of a scale. If the data holds up, it could mean that our assumption about large-scale homogeneity might need revision. Neither of these two ultra-large structures is easy to explain in our current understanding of the universe, says Alexia Lopez, the scientist who discovered them. Their enormous sizes and unusual shapes must surely be telling us something important. But what exactly? One possibility is that such superstructures are statistical flukes, random clumps that by coincidence turned out to be larger than expected, but the likelihood of discovering not just one but several gigantic structures Others include the Sloan Great Wall, the South Pole Wall, and the massive quasar groups. It becomes increasingly small. Another intriguing idea is that they hint at new physics or new aspects of the universe's initial conditions. Perhaps some exotic process in the early universe gave rise to these megastructures, going beyond standard inflationary cosmology. For example, cosmic strings, hypothetical ultra-thin defects in space-time left over after the Big Bang, could, if they existed, have influenced the distribution of matter on enormous scales. These are speculative objects, but they represent the kind of new physics scientists invoke to explain such anomalies. A different idea proposed by the renowned physicist Sir Roger Penrose is even more radical. He suggests that these structures might be signs of a universe that existed before the Big Bang. In Penrose's conformal cyclic cosmology, our Big Bang was not a beginning but rather a transition between cosmic aeons. If true, then traces of the previous universe could appear in our own universe. Penrose even suggested that ring-like imprints in the cosmic microwave background could be evidence of gravitational waves from the collapse of an earlier universe. Although most cosmologists are skeptical of such claims, the very existence of such objects forces us to consider that we may not fully understand the physics of the early universe. Let's summarize what we know so far. The Big Bang marks the starting point of the universe's expansion, and for the first few billion years, this expansion slowed due to gravity. But in 1998, researchers made a shocking discovery. The expansion was actually accelerating. Something unknown, later named as dark energy, was pushing the cosmos outward, overcoming gravity on large scales. To this day, dark energy remains one of the deepest mysteries in cosmology. We know it makes up about 68% of the universe's contents and acts as a kind of anti-gravity driving galaxies apart. For decades, the simplest assumption has been that dark energy is a cosmological constant, an unchanging property of space itself, possibly linked to vacuum energy. In our best model, the so-called lambda CDM model, where lambda stands for the dark energy, this force remains constant over time, leading to the universe accelerating exponentially forever. However, very recent data suggests that this may not be the whole story. Data from the Dark Energy Spectroscopic Instrument, or DESI, which has surveyed millions of galaxies and quasars, indicate that dark energy's influence may be evolving over cosmic time. In early 2025, scientists analyzing 3 years of DESI observations reported new evidence that dark energy has weakened over billions of years. In other words, rather than delivering a constant push, dark energy's repulsive effect may be gradually decreasing. The DESI results tantalizingly hint at an evolving dark energy, says Dr. Arjan Day of NSF's Noir Lab. If it's true, this would dramatically shift the picture. It could mean that the universe's acceleration won't continue indefinitely. In fact, as one researcher noted, whatever is causing the universal expansion may be decaying or decreasing in strength. This raises major questions about the fate of the universe. Will acceleration eventually slow or even stop? Could gravity ultimately regain control, leading to a slowdown in expansion or even a future collapse? We don't know yet, but it's clear that the once established idea of constant dark energy is now under scrutiny. Just like the nature of dark energy, another invisible foundational component of the universe is under close investigation: dark matter. Dark matter, invisible except through its gravity, is believed to form the scaffolding for galaxies and clusters. It plays a critical role in our simulations of structure formation. Without it, we can't easily explain how galaxies formed so quickly in the early universe. However, despite decades of searching, dark matter particles have never been directly detected, and their true nature remains unknown. This has led some scientists to explore bold alternatives to the standard Big Bang model that would eliminate the need for both dark matter and dark energy entirely. This bold proposal came from Dr. Richard Liu, a physics professor who in 2025 put forward a new model of the universe that questions the very idea of a single Big Bang. According to Liu, the universe's expansion and the formation of cosmic structures could be explained not by one event, but by multiple mini-bangs or transient singularities that occurred sequentially. Instead of a single initial explosion followed by a continuous acceleration driven by dark energy, Liu suggests that stages that manifest as bursts of energy and matter entering the universe at different times might explain what we observe, effectively replacing both dark matter and dark energy with those sudden acts of creation. During each of these bursts, matter and energy flood the cosmos uniformly everywhere at once, and then the singularity winks out. These bursts occur so rarely and rapidly that we wouldn't observe them directly. They resemble cosmic flickers that leave behind shifts in the rate of expansion and give rise to new structures. Between the bursts, the universe coasts along with no need for any mysterious dark energy permeating space. The idea is striking because it effectively revives aspects of the old steady-state hypotheses, which propose the continuous creation of matter, but in a way that doesn't violate conservation laws. Liu points out that unlike the classical steady-state model, which was deemed impossible because it required continuous creation of matter from nothing, thus violating energy conservation, his transitional singularities appear and vanish so quickly that they circumvent such violations. For an infinitely brief moment, a burst adds mass energy everywhere and then disappears. Interestingly, this can be formulated in a way that doesn't violate physics as we know it, though it certainly stretches it. The effect of these temporary singularities would also create a kind of negative pressure within the structure of the universe, much like dark energy does. In essence, each burst could trigger a period of accelerated expansion, solving the dark energy puzzle for that era and also seeding fluctuations that lead to galaxy formation, addressing the role of dark matter. According to the paper, the Big Bang itself might have been just the first in a series of such bursts, the one that started it all, followed by others. In the standard model, there was only one singular creation event. In Liu's model, there are many. This is a radical departure from conventional thinking, and naturally, at this stage, it remains speculative. How can we know whether it's true? The scientists suggest looking for characteristic patterns in the data. For instance, barely noticeable jumps in the redshift, distance relationship for distant galaxies. If the universe experienced multiple expansion bursts, then faraway objects might not line up in the smooth curve we expect from a model with constant dark energy. There might be small discontinuities corresponding to these ancient bursts. Whether or not this particular theory is confirmed, its very existence highlights an important point. The Big Bang model, despite its immense success, still holds mysteries, and solving them might require moving beyond the idea of a singular beginning. But let's return to the main question: what if the Big Bang wasn't the ultimate beginning? Modern cosmology allows for this possibility. We've already encountered Penrose's idea of a cyclic universe, in which our Big Bang is merely the most recent in an infinite chain of universes, each born from the dissolution of the one before. In this model, in an unimaginably distant future when the universe has continued to expand and all matter has eventually decayed, it would enter a near-empty state, which, curiously, begins to resemble the extreme conditions of a new Big Bang. And at that moment, a new aeon could begin. It's a brilliant attempt to link the end with the beginning, though it hasn't gained widespread acceptance. Interestingly, Penrose claimed to have discovered concentric circular patterns in cosmic microwave background data, which he interpreted as imprints of gravitational events that predated our Big Bang. However, most experts remain unconvinced. Still, the concept of a cyclic cosmos is not new. Ancient philosophers envisioned eternal cycles and some modern alternatives to the Big Bang, like the acypriotic universe model that involves colliding branes in higher dimensions, also envision a bounce instead of a single beginning. These theories offer one answer to the question of what came before. Something did. Another universe, another cycle. Another line of thought suggests that perhaps time itself began with the Big Bang, meaning that the question of before might be meaningless. It's like asking what lies north of the North Pole. For a long time, this was the orthodox interpretation of general relativity. T equal O. Our equations break down, so we could say that time simply didn't exist before that. But quantum physics pushes those boundaries. Some models of quantum gravity, such as loop quantum cosmology, propose that the Big Bang could have been a big bounce, where a previous universe collapsed and then rebounded into ours. In these models, time continues through the bounce, so there was a before, namely the pre-bounce universe, of which we might even find traces in our current cosmos. It's a compelling idea that perhaps the Big Bang was a transition, not a creation from nothing. If dark energy really is changing and might eventually reverse, as DESI results suggest, we can imagine our universe one day contracting, ending in a big crunch, which could spark a new explosion. Of course, this is only speculation, but it shows that the boundary between before and after the Big Bang is a topic of active and serious research. The evidence we have today paints a picture of a universe that's surprisingly well described by the Big Bang theory, yet at the same time full of surprises that challenge it. As for now, the question, what was before the Big Bang, remains unanswered. It lies at the very frontier of scientific understanding, where empirical data is scarce and imagination collides with rigorous mathematics. Yet, as we've seen, science is making remarkable strides in illuminating the earliest chapters of cosmic history. Will we ever find direct evidence of a reality before the Big Bang? Perhaps not directly, but indirect clues may emerge. If our universe is just one of many cycles, then maybe future observations of the cosmic microwave background or galaxy distributions will reveal subtle patterns left behind by a previous cosmic cycle. If the Big Bang was one in a series of bursts, then we might find fossil imprints of those fleeting events in the data. Or perhaps one day a new, unified theory of quantum gravity will allow us to deduce the state of existence that gave rise to our universe. Which scenario do you find most plausible?